been teaching for 28 years. I think this is only the second time I failed to get a midterm graded within a week. I'm really, really sorry. I'm going to do everything I can to have the coding portion done by tomorrow evening. The TA told me he is struggling more with it, so he should have it ready for me by to hand back on Tuesday. But I'm really, really sorry that I did not get the midterm graded. I'd really like to have things turned around within a week. So at any rate, but like I said, I will do everything I can to have the coding portion graded by tomorrow evening. Second thing, today we are going over a recursion technique that is very helpful to you on Lab 9. And actually what I'd like you to do is take a few minutes and read through the lab description for Lab 9 right now. Because even though we're going over a different problem, we're going over Sudoku rather than what you see on Lab 9, the technique that we're using today is the technique that you need to use on Lab 9. Okay, so just take a few minutes and read Lab 9. So this is a game that Dr. Planck liked to play when his daughters were young, play with them. And it's sometimes would be frustrating because he couldn't figure out exactly how to apply the shapes. So he wrote a program that would show the order in which you should apply the shapes. And then figured out that it was a great program for a lab because it illustrated one of the ways you use recursion. So with this game, you can see that he applies the shapes and he does it in a way that causes all the shields to eventually turn to swords. And if we're trying to do this with a computer, the thing is we can't just kind of randomly apply the shapes to different parts of the grid because there's literally, when you have a huge number of shapes, even a relatively small number, the number of ways that you could apply them is roughly the number of grid cells to the nth powers. Is that true, or is it just 9 times 9? Yes. So here, there's literally 9 to the third ways that you could apply the different shapes. You could apply the first shape to any of these 9 cells. Then you could apply the next shape to any of the 9 cells, and so on. So that's 81 times 9. That's about 729 different ways you could, combinations that you could use just to apply 3 shapes to this grid. Keeping track of all the combinations you've used can be quite difficult unless you've approached the problem systematically. And recursion gives us a way to approach this problem systematically. Basically, we are going to start at the upper left corner with the first cell, and each time we apply a shape, we're going to start at that upper left cell. And then we are going to apply the shapes in a left to right, top to bottom way. So if applying the first shape to the top left cell in the end does not work out and we're not able to convert the entire grid to swords, we'll move in a systematic way to the second element in the grid and do the same thing. So this kind of problem is an example of a problem that uses backtracking to solve the problem. So you try out some ways of changing the grid and then if it doesn't work, you backtrack to a previous state. And the second characteristic of this problem is that there's some constraints. In this case, the constraint is that we want to change all the shields to swords. We have to apply these shapes in a specific order. So we have to apply this shape, this horizontal one first, then this shape, then this shape. And finally, the third constraint is when we apply a shape, it flips the swords and the shield. So a sword becomes a shield becomes a sword, much like exclusive OR. Okay, the problem that we're going to consider is got the same kind of characteristics, but it is Sudoku rather than the shapeshifter problem. But the way you solve it is going to be the same approach, which is to use backtracking. So for those of you who have never encountered, I'm just curious, who has not seen Sudoku? Okay, good. So you've seen it. If you're not, if you need a quick review, here it is. You're given this 9x9 grid, and the 9x9 grid is separated into 9 panels, 3x3 panels, which you can see by the thicker lines. And your goal is to fill in the grid so that every row has the numbers 1 through 9 with no duplication. Every column has the numbers 1 through 9 with no duplication. And every panel has the numbers 1 through 9 with no duplication. So just like the shapeshifter grid has some constraints, those are our 3 constraints here. No row has a duplicate value, no column has a duplicate value, no panel has a duplicate value. And just like the shapeshifter problem, we need to approach solving the Sudoku puzzle with the computer in a very systematic way. And one way you could do that, let's think about it. What if you start at the upper left-hand corner, what number do you think you might try first here? 1, because the numbers can be 1 to 9. And the first thing you would do is, would you immediately say that 1 works, or would you do some checking? You would check. You would make sure that there was no 1 yet in this row, no 1 yet in this column, and no 1 in this panel. So in fact, you would find that that was temporarily okay, so you'd put a 1 there. Now, if we're doing it systematically, we move to the second cell in the first row. And the first value, if we're just doing this blind, okay, not with us, we're certainly not going to try 1, are we? Because we can see that we used 1. But if we're doing this systematically with the computer doesn't get to look around. The computer has tunnel vision. And it can't see what anything else is done yet. So what number do you think the computer will use if it can't see anything? 1. Nope, it will use 1. It can't see anything. So it will try 1, and as we can see, it's no good both because it's duplicated in that row and it's also duplicated in that column. So next we will try 2. Is that a good number to try? Why not? It's in the column, the row, and the panel. It's 0 for 3. So now we try 3. Any good? Nope, same row. So we try 4. Any good? Nope, because column. We try 5 and it's a winner. Okay, 5 doesn't have any thing yet. So now we go to the next row. The next cell. We'll try 1 again. It's no good. We'll try 2 again. It's no good. We'll try 3 again. It's no good because over the row. We'll try 4. And 4 is a winner. Okay, so we move on to the next cell. We don't move down in the panel. We move into the next panel, but continuing on the first row. And again, we try 1, it doesn't work. We try 2, it doesn't work. We try 3, it doesn't work. We try 4, it doesn't work. We try 5, it doesn't work. We try 6, and 6 is a winner. Okay, so then we would try, again, we would move to the next cell. We try 1, 2, 3, 4, 5, 6, 7 is the first one that works. Now, we next encounter some cells that are filled, so we can't change them. So we move on to the next unfilled up cell, and you can see that the only value that would work would be, if you were just considering the row, 8. But does 8 work? No. So this is where we have to backtrack. So we now backtrack to the first value, to the last cell that we filled. And the last cell that we filled was 7. And we ask, is there another value that we can try rather than 7? And the answer is yes. We can still try 8 and 9 here. So we'll try 8. Okay, 8 works. And we could then put 7 in here, and you can see that that's still working. But you'll see that eventually this approach will fail too. How do I know that this approach also eventually failed? Because on the right-hand side, I see that 8 and 7 were the ones that eventually. So I know that eventually what happened is I actually backtracked all the way back to this one, and that I had to try 8 here. And that then I subsequently, let's see, tried 6. But 6 was not a winner, so then I eventually tried 7, and that turned out to be a winner. So you can see that what I have to do is I'm systematically moving left to right, top to bottom, which is what you'll do in the shapeshifter problem. And I'm also systematically trying values here. Now in the shapeshifter lab, there's the pattern either works or it doesn't. Here, there's 9 possible values you can use. But in both the Shapeshifter Lab and this example, when we backtrack, we have to make sure that we restore the grid to its original state. So for example, I originally had 6 and 7 here, and then I tried to put something here and it failed like 8. When I leave this position, I need to restore the grid to its original state. So I do so by changing it back, in this case, to an empty cell, which is denoted by a dash. And then I come back to here and I change its value. So that is what we are going to be doing here. And this is recursion. Okay? We'll show you how. Well, actually, the reason it's recursion is because what I'm doing is I'm solving one small part of the problem. So when I start out, I'm starting by trying to put a value in there. Once I have filled in a value here, which I put a 1 here, I now try to solve the remaining part of the puzzle. So that's the recursive subtask, is to solve the remaining part of the puzzle. Now, you also have to figure out what the base case is. So I'll give you a moment if you can figure out, what do you think the base case is? So it's, but how would you test that there's only one possible value per square? So you have to think about that too. There's kind of, it's a good guess. I'm just. The entire grid is valid, and so you're right. The base case is the entire grid is valid, which is kind of what I think you were getting at as well. It turns out that if you get to the end and have nothing left to do. So the base case is kind of like when you get to it's now empty, or you have, so here the problem still had 80 cells left to solve. There's 81 cells in the grid. There was still 80 left to go. When you eventually get to this point where you fill in the 3 and you try to advance to the next cell, there's nothing left. It's like what you have left to do, 0 cells. So in some sense, it's when you step out or past, when you try to get to row 9, so if we number our rows, when we try to get to row 10, when we try to get to row 9, effectively we have solved the puzzle, because at this point we have put a valid number in every cell. Okay, so the base case is a little harder to see in this case, but in some sense it still is when we reach an empty problem. Normally the base case is when we have reduced the problem size to a 0 problem size, or something that has only 1 or 2 elements. And that's the same thing here. The converse of saying all of the cells are valid, the converse of that is there are no empty cells left. So there are no empty cells left would be the base case. Okay, so let's go through and see how we solve this thing. And again, the way to do it, we've tried all semester to emphasize the importance of using an incremental approach. So you can't actually implement the recursion until you've read in the puzzle. And it really also helps for debugging if you're able to print out that grid before you do anything else. The same with the Shapeshifter lab. It really helps if you first read the grid and then are able to print it for debugging reasons. So the first things we're going to do is actually implement functions for reading the grid and printing it. The next thing we're going to do before we even try to solve it is we're going to write functions that allow us to check to make sure that when we add a value to a cell, that it's a valid cell. We also do that because we want to make sure that the puzzle we read is valid. We don't want, maybe we're reading a puzzle that already has an invalid layout, where 2 values are in the same row, the same column, or the same panel. Only after we've kind of written this introductory stuff will we attempt to actually solve the puzzle using recursion. So he's done that. Print screen is an ASCII version that prints it out. And print convert is something that we're not going to go over. It creates a JPEG image. So these are JPEG images that you see right here. And the print convert is printing it in a way that can be fed to a program called convert that will convert it to a JPEG. Print screen is just going to use ASCII printing with cout. So it's going to print it like this in nice little panels with the dashes representing empty cells. Okay, solve is going to be our recursive function that tries to solve the puzzle and returns true if it can be solved and false otherwise. Now you'll notice that these functions are protected, which means we don't want the user to be able to access these 4 functions. So the first 3 allow us to check the validity of a cell entry. The 4th one is going to be called by solve in order to solve the recursion. Okay? Then we want a 9x9 grid to hold our integer values, and we'll get to this integer array when we need it. So don't worry about it just now. So we'll start with the constructor and with print screen. The constructor is simply going to read the problem from standard input. And the way that the problem is going to be presented is with, does he have a, there we go. So he's going to give us 9 lines, 9 characters per line. There's 10 valid inputs, the digits 1 through 9, and the dash. Anyone see an issue with this particular puzzle? It's got an X in it, so we need to also check for bad input. Now, there is no guarantee that the puzzle will be presented like this, just that it will have 81 characters. So when he reads it, he doesn't use getLine because there's no guarantee that there will be 9 characters per line, although that's the obvious way to present the input. Instead, he's simply going to read 81 characters. So he is going to read a row at a time. The second one is reading each column in the row. So this is reading read a row, read each column in the row. And C is a character, so if he fails to read a character, that means there were insufficient characters. So he prints the error message, bad Sudoku file, not enough entries. Otherwise, he checks to see if the character is a dash, and if it is, he knows that's an empty cell, and we're going to represent an empty cell as -1 because that's an invalid value. Otherwise, we check to see if the character is between 1 and 9, and we use that trick of subtracting off the character 0. Does anyone remember why we can do that to get a digit? ASCII. So characters are in ASCII, and the digits 0 through 9 have consecutive ASCII codes. So if we subtract the ASCII code for 0, that will give us the digit in integer format. So we do that. Otherwise, we know we have an invalid character, so we print the fact that we have an invalid character. So that is very simple. That's the constructor. It's simply reading in the file from standard in. Okay, and just with this, it's able to catch this first bad file, but it's not going to be able to catch any of the other ones. And I see, actually, this should be bad 2, bad 3, and bad 4, not bad 1, and bad 1. So the next thing we need to do is create something for printing out the grid so that we make sure that we have properly read it. No guarantee that you properly read it. First thing you should do is check, print it out, make sure you properly read it. So the second function we implement is print screen. Okay, and it's the same basic idea. We're going to print a row at a time, so 1 row per line, and then we print each column in the line. So this first line is saying put a space between each of the entries, except if it is the first column. We don't want to put a blank before the first column. Okay, obviously if the grid cell is a -1, we want to print a dash, and we follow that with a blank space. Otherwise, what we want to do is print the character itself with a blank space. And then when we get to the end of a panel boundary, so remember we use 0 indexing, so 0, 1, 2, those columns should go in a panel. 3, 4, 5, they should go in a panel. So we're printing a little more space between the panels. And you'll see that we also print an extra new line character when we reach the end of a panel on the row. Okay, so when you see it, you see there's actually 2 spaces between every entry. That's why there was one space here, whoops, and one space here. Okay, and you see there's extra spaces between the panels, extra row. Whoops, I can't do it, but there's an extra blank row between them. So a nicely laid out thing. I strongly recommend when you implement Lab 9, you do it the same way. You read your grid, you print it out. That's the first thing you do. You don't do anything else. Okay, make sure you've read it and that you can print it out. Okay, so when he runs it on the first bad file, it finds the bad entry. You can see at this point he's still not checking for bad rows or bad columns, but at least it's able to print them out. Okay, second thing, checking the input. When you're doing your Lab 9, what I would suggest you do as your second step is that you be able to apply a shape to the grid and make sure that when you apply the shape, it correctly modifies the grid. So when you're doing Lab 9, what I would probably do is first I would make sure that I can read and print the grid. The second thing I would do is I would make sure that I could apply a shape correctly. So I would try writing my function to apply a shape, and I would make sure that when I try it with a few shapes and print it, it prints it correctly. Okay, here we're writing the functions that are also making sure that we can apply a value correctly. We're going to write the functions as row valid, as column valid, as panel valid. So we're doing essentially the same second step, making sure that we can apply a change to the cell correctly. So I'm trying to show you the similarities between this and Lab 9. Okay, so to check whether a row is valid, this is where our checker array comes into play. So you remember back here, we had this bool checker. You'll see it has 10 entries, not 9. So what he's doing is he doesn't want to have to worry in this case about the zeros because he's representing the numbers that get stored are the numbers 1 through 9. He's not storing 0 through 8. He's storing 1 through 9. So what he wants to do is when he checks the row, he wants to know whether he's already seen 1, whether he's already seen 2, whether he's already seen 3. So initially he hasn't seen any of those digits. So he goes from I equals 1 to 9. He sets all the values to false. Thereafter, he goes through whatever, this is the row he's checking. So he's going to go through all the columns in the row. And for each column, he's going to first say if the column is not equal to -1. So if it's equal to -1, it's valid. It's okay to have an empty cell. Okay, but if it's not empty, then he's going to check to see whether he's already seen that digit. If he's already seen that digit, he returns false because the row can't be valid. If he hasn't yet seen that digit, he sets that entry to true to indicate, okay, I've now seen that digit. So pretty simple. And if he gets to the end of his loop and he hasn't returned false, then the row must be valid. Okay, he's gotten through all 9 columns without seeing a duplicate. So he returns true to indicate that the row is valid. Okay, so a couple things here. First of all, he could have simply declared checker right here. Why don't you think he did that? Why do you think he made it a an instance variable rather than just making it a local variable? Because this would be the normal way to do it. Because the checker array isn't needed anymore after we have finished checking the row. We can throw it away. Why keep it around? Well, but we're filling in the table constantly. So it really isn't, in some sense, needed anymore. You don't need the values. In fact, you can see every time I re-enter, I set all the entries to false. So clearly, I don't need to retain the values. Okay, yes?
You needed to reconstruct what you had before you messed up if you put a wrong in there?
Nope, it turns out you don't need it to reconstruct either, but it's a good guess. Okay, the reason actually just has to do with efficiency. Okay, he simply does not, it takes time to constantly allocate and deallocate an array. And he's going to need to use this array constantly. He needs to use it in his row valid, his column valid, and his panel valid. So the only reason he's doing it is he doesn't want to waste a lot of the computer's time constantly allocating and deallocating the array. This is kind of very subtle, but he did it this way, and I want to explain why he's doing it, because there would be nothing wrong with declaring checker to be a local array for each of the three functions. In fact, that is probably how you would do it if you hadn't seen him do it this way. So it's purely an efficiency thing. He, in essence, wants to share this array amongst his three checking functions. Okay, and he declares it to have 10 entries. He's not worried about the one wasted space. The 0th entry is never used, but the amount of wasted space is so minuscule that it's outweighed by the convenience of not having to always subtract 1 when we're checking our grid. We don't want, our numbers are 1 to 9, not 0 to 8. So it's a lot easier if we can just leave them as 1 to 9. So he makes it 10 entries. He always ignores the 0th entry. Okay, is column valid is essentially the same as is row valid, except we're going through a column. Is panel is just a little bit different because now you're checking multiple rows and multiple columns. So you have a start row and a start column, but it's really not that much difference because you're simply checking 3 rows, and within each row you're simply checking 3 columns. This isn't all that much different from what you did in some of your early PGM labs when you had to create checkerboards. So any questions about the error checking? Okay, so once he's done the error checking, he again tests them. So don't just write them, do a little checking. So in fact, when he has done them with his bad input, he checks to make sure that it actually is checking things. It's no good to write your error checking stuff and not check it, because then if it's wrong and you start writing the recursive solver, you won't know whether the recursive solver is wrong or your error checking functions are wrong. Same thing with why I tell you to write a function in Lab 9 to apply the pattern, then run a few patterns through it to make sure it's changing them properly. Because if you don't do that, and then you immediately write the recursive solver and it doesn't work, you won't know where your code is going wrong. Okay, and I'm still getting that a lot, which is my code's not working, I'm not sure where the bug is, and I often think that's probably because you didn't incrementally write your program, because if you incrementally wrote it, you would have only probably added a few lines of code, you'd be pretty sure where the bug was. Okay, so let's say that we have done our checking, we found that it works. So now we're finally ready, and notice he's up to his 5th version. So this is version 5 before he's even getting to the recursion. And the first thing he does is it's a very simple call for the solve function. He simply calls recursive solve and says you're to start at the upper left corner. Remember, something like that happened the other day too. I told you to solve palindrome. And really, from the user perspective, they just want to give you a string. They just want to basically be able to give you a string S and have it return whether it's a palindrome or not. Do you remember, though, what I added to make your job easier? You start and end. But the user shouldn't have to do that because that reveals too much of the implementation to the user. The user just wants to call palindrome. So really, what you would also tend to do is write a second function called bool palindrome helper. Which would take a string S and an int low and an int high. And all that palindrome would do when you implemented it is that it would call palindrome helper. Okay, passing it S0 and 0. So this is a common technique with recursion, because often with recursion, you need to know some additional parameters, but the user shouldn't be bothered with those additional parameters. So for the user, they just are given a function with whatever input has to be provided. You then write a recursive helper that may take additional parameters. Okay, so that was true with palindrome. It is true here with his solver. He really needs to know which cell he is supposed to be starting his search at. But that's none of the user's concern. Okay, so we said we were going to do a systematic search with our solver. So the first thing it has to do is it has to find an empty cell. There's no guarantee that 0, 0 is an empty cell, or whatever we pass in is an empty cell. So the first thing we do is we try to find an empty cell. So while the row is less than 9 and our grid entry is not equal to an empty cell, we increment the column. If we get to the end of the row, we increment the row and reset the column to 0. Okay, and if we get to the end of the grid, that means that we will step out by becoming row equals 9. So this is the base case. If we get down to here, we return true. Okay, so that is what we are doing. Now, this isn't the entire function yet, but this is the start of it. This is just trying to find an empty cell. When we come out of this loop, there's one of two situations. Okay? So we either have found an empty cell, or there are no empty cells left. Okay, this one takes care of the case where there are no empty cells left. And if there are no empty cells left, we know that we must have a valid solution. Otherwise, we will soldier on and we will move to the next step, which is what? If we found an empty cell, what should we do next? Try to put a number in it. So now we're going to try each value between 1 and 9. This is not, so this is try each value between 1 and 9. Okay, so we set the grid to that value. Then we check to see if the row, the column, and the panel is valid. And if any of them is not valid, we'll immediately, we won't execute the return true. If they're not valid, we will simply increment I to the next value. If all three of them are valid, remember this is conditional and, so if only if all three are valid will we call the recursive solver with R and C. Okay? And if the row is valid, the column is valid, and the panel is valid, and we can recursively solve the remainder of the puzzle, then we return true, because that means that setting the cell to this value successfully solves the puzzle. Okay, if it doesn't, we come back up and increment I to the next value. Now, there is this cute little trick here. That may look a little funny. R minus R mod 3, C minus C mod 3. What does that mean? Well, we need to know what is the starting row and the starting column for this panel. So for rows, if we have, these are the rows, and this is the start row. So if we have rows 0, 1, and 2, what is the start row? 0. For rows 3, 4, and 5, what is the start row? 3. And for 5, 6, and 7, 6, 7, and 8, start row is 6. So what we have to do is find a way to convert all the values 0, 1, and 2 to 0. We need something that maps 3, 4, and 5 to 3, and we need something that maps 6, 7, and 8 to 6. Okay? So what he is doing is he realizes that essentially each of these is getting back to something that is divisible by 3. So 0, 3, and 6 are divisible by 3. So what he's doing is he's simply subtracting off the remainder. And that will give him his start row. So no matter what, if we subtract off the remainder, if we divide 4 by 3, the remainder is 1. When we subtract 1 from 4, we get 3. So he's basically just subtracting off the remainder, and that's going to give him his start row and his start column. So again, you see the value of mod. Mod comes up a lot. It's just nice to have these little tricks with mod. Okay, so that's what's going on there. He's just getting the start row and the start column by subtracting off his remainder. Okay, so this was successful. He returns true. Now let's say he falls out of this loop. If he falls out of this loop, you know you have failed. Okay, you tried every one of the values and you were never able to return true. If you couldn't return true and you tried all 9 values, you failed. So you have to backtrack. When you backtrack, you must restore the grid to its previous values. And the way we do that is we reset the grid to -1. Now, in Lab 9, it's not quite that simple. So in Lab 9, the failure case, Remember in Lab 9, let's go actually look at Lab 9 quickly. Okay, so it turns out he applied the active shape to the first row. He got this. What do you think you're going to have to do if you find out that the first shape cannot be applied to the first row and succeed? You have to unconvert it. So in Lab 9, the failure case, so in Lab 9, when you fail, you must undo the shape or the effects of the shape. Okay, which is pretty easy because again, it's just a flip. And if you want, I'm not saying you have to do it, but bitwise exclusive OR works pretty nicely because you can, I'm not saying you have to, but I'm just pointing out that if you represented the shields as, say, zeros and the swords as ones, as bits, then applying exclusive OR, if you have a shape, this is 0, 1, 1, if you apply a shape, in this case it was, the way to represent that shape is as a matrix that is 1, 1, 1. 1, 1, 1 applied once gives you 1, 0, 0. When you apply it again, it undoes it and gives it back the original. So if you apply exclusive OR twice, it returns you to the original value, which is kind of cute. Not saying you have to use exclusive OR because that says something about how you would store the shields and the swords. You'd store them as bits, but certainly exclusive OR is a nice way to flip something and then flip it back. And it's a common trick used in my area, which is graphical user interfaces, because in graphical user interfaces, you often have feedback objects like this cursor, right? The easiest way, it turns out, to move a cursor that's very fast is to exclusive OR it onto a screen, and then when you draw it the second time with exclusive OR, it makes it disappear, which is pretty cute. Okay. So coming back to here, this was our failure case. In the failure case, we have to restore the grid to its original form, which we do both here and in Lab 9. Okay, and that's it for this particular problem. When we run it, it successfully solves the puzzles. And I'm not sure if he has any that are, yep, he doesn't. He doesn't have any that are not solvable. All the puzzles he gave were solvable. And it actually runs pretty quickly, although there are certain puzzles for which this program can take an awfully long time. If you tried to analyze how much backtracking could possibly be done, well, you could get all the way to the very last entry, the 81st entry, and find out it doesn't work. Actually, you can't really. Probably if you get to the 80th entry, you'd find out it doesn't work. At any rate, you might have to backtrack all the way to the first entry. And if you start looking at it, the time to run is something like 9 times whatever it takes to run on a, if the input is, if you have n empty cells, okay, you may have to run the recursive solver when you fill in one cell, you have n minus 1 empty cells left, and you may have to do it 9 times, one for each of your 9 values. Okay, so does anyone have a guess as to what is the potentially worst case running time for this? A lot, yes, but we can be a little more precise than a lot. If you gave you all empty cells, it would be 9. So let's just try it with 3. So if it's 3, it's 9 times t of 2. T of 2 is 9 times t of 1. Pardon? It's not n factorial because that would be 9 times 8 times 7. This is 9 times 9, in this case times 1. If it was 3, it would be 9 times 9 times 9 times 1. 9 to the n. That's terrible. So there are certain puzzles on which this thing will take an awfully long time. Okay, for those of you who enjoy doing Sudoku, which do you think are the puzzles that it's going to take the longest on? Pardon? Well, just say you're given a puzzle. There's a certain kind of, okay, is it going to be an easy puzzle or is it likely to be a hard puzzle? And if you're thinking, if you can tell me what is going to take the longest amount of time on, what is the feature of that puzzle that is going to make it run the longest? Is what? Pardon? Yes, the hardest puzzles are the ones where they give you the fewest numbers, right? It's where you have the least inferences to make. So it's precisely the time you're going to run this thing because you're most likely to run it on the hardest problems. The hardest problems are the ones where they give you the most empty cells. So that's where it could get really bad. So again, remember the Fibonacci numbers? That was exponential. This algorithm most of the time runs blazingly fast, but I'm just pointing out in the worst case, not so fast. Okay? And you could be cruel. I mean, you could give someone, well, I could concoct them. I know that it's possible to concoct really nasty ones. Okay, so questions about this. You're going to be doing something similar in Lab 9, so hopefully you saw the general flow of things. Yes?
Just out of curiosity, if you did, like, if your input was just 81 dashes, would the program come up with, like, different
Yes.
solutions?
So the question was, let's say you input 81 dashes. In that case, there are multiple possible solutions. Your program will only produce the first one it finds.
Will it be the same one every time?
Yes. It's deterministic. It will always find, because it's not using random numbers. It's systematic search. So it will always, if you give it 81 empty cells, it will start with 1. I guarantee you the solution will have 1 in the first cell. It will have 2 in the second cell, 3 in the third cell, 4 in the up to 9. The second cell is going to have 2 in it. Okay, so so try it and you'll see it always comes up with the same solution because it's systematic. Other questions about it? Okay, so we spent 2 days on recursion, and so far you've seen 2 of the 3. I've got one more example for you today, but you've seen there's 3 fundamental ways you use recursion. Okay, the first way is the way we did it on Tuesday. So on Tuesday, we were simply breaking a problem. We break a problem into multiple pieces. Okay, solve the smaller pieces. and recombine the results. Okay, and this is good for parallelization. Okay, so good for parallelization. It's not the only thing it's good for. Like the palindrome example, that wasn't really something you could parallelize, but you were still breaking it into a smaller piece. Today we looked at something different. We looked at systematic search with backtracking. So that's a second kind of thing we do with backtracking. And the systematic search might be subject to constraints. Systematic search subject to constraints. So recursion is very good for that. And unlike in one, there's often a nice solution that uses loops. That's not true with 2. With systematic backtracking or systematic search with backtracking, it's very difficult to write that kind of problem with a loop. I challenge you to try to write the Sudoku solution with loops. You will find that you very quickly bog down. The third thing is what we're going to start into next week, which is systematic search through recursive data structures. Like trees and graphs. We are going over trees in the final 3 weeks of this course. Graphs you will see in 302. So these are kind of the 3 fundamental uses of recursion. And 2 and 3 are a little bit similar, but 2, you're normally not using a so-called recursive structure. Our grid wasn't really recursive. If you're wondering what are some other examples of systematic search with backtracking, so number 2, mazes. You can, if you want to get through a maze, using recursion is a very good way to do it. With a maze, you normally have 4 choices. You can go forward, you can go to the left, you can go to the right, you can go backwards. Okay, so it turns out in a maze, you can try each of those 4 possibilities, and if you, let's say you start by going forward, and you find out I mark forward, and all of a sudden I'm surrounded on 3 walls, I back up. I still have 3 more directions I can search, left, right, and back. So mazes are something that can be solved with systematic backtracking. Games, checkers, chess are games that can be solved with systematic backtracking. Now, they are so complicated that to fully solve the position takes too much time. So they only go some number of levels deep before they back out. Same thing with backgammon, same thing with Go. All these different board games, they go to a certain depth and then they backtrack back and they return the best solution they have found. Okay, it turns out that that is somewhat what the Towers of Hanoi was doing. We didn't really go over it, but in fact, the Towers of Hanoi from last lecture, whoops, I didn't have the, but with the spindles, okay, what you are able to do is essentially you move the top n-1 elements to 1 spindle. So you solve the problem for n-1 elements. Then you move the bottom element over, and then you move the n-1 elements back. So it's essentially a backtracking thing. Okay. And then 1's harder to characterize. There's just a lot of different ways. I gave you a number of examples with 1 last time. I gave you the example of the Fibonacci numbers. I gave you the example of summing up an array by breaking it in half. I gave you an example of doing a sort by moving all the smaller numbers to the left, all the bigger numbers to the right, and then sorting the 2 halves. So the toughest one in some sense is 1 because there's no, boy, that noise bothers me as much as it probably bothers you. Okay, we're wrapping up. So 1 is the hardest because there's no systematic algorithm that solves all instances. 2 and 3 are a lot easier because it's kind of like the same algorithm always works with just a few minor modifications. So with Lab 9, you can use approach 2 for the first problem, or I'm sorry, for the second problem. And for the first problem, it turns out in Lab 9 that the first problem is, let's get to it. The first problem, enumerating strings, is really an example of the first type, where you're breaking the problem into smaller parts and you're solving the smaller parts. And the trick with the first category of problems is figuring out what the smaller part should be. So once on part 1, the whole problem is going to be figuring out what are the 2 smaller parts. And I'll give you a hint. The TAs will give you other hints, but for part 1, it will be there are 2 smaller problems that you will have, that you will be solving. Okay, so you'll basically write problem 1 as 2 smaller problems that you solve. Okay, so with that, I will turn you loose. As I said, the final 3 weeks starting next Tuesday.